Good evening, everyone. Today we are on the fifth day of our workshop and with the sixth lecture, how to derive the KdV equation. Now, first let's start with the basic equations. The governing equations in a normalized form. Even if it's not normalized, we are just here to learn the process in a very simple way. The normalized equations are, the first one is the continuity equation, the second one is the momentum equation, and the third one is the Poisson's equation. Now in the first equation you find that we have got the density times the fluid velocity, that's the current, and here we have got the electrostatic potential and the stress tensor P. It is also sometimes we call it the equation of state. So you find that for suppose we have a polytropic process where the pressure is proportional to some exponent of density m. Okay, so it is, you see, it is a n to the power gamma, suppose, where a is a constant. Now here in the stress term, as we find here, 1 by n dp dx. So we just expanded this 1 by n dp dx. P was given through this expression. So we find here that you can see a gamma n to the power gamma minus 1 del n del x by n. So it simplifies into gamma minus 1 a n to the power gamma minus 2 del n del x. So let's make a bit well. Now here we have got the perturbation expansion. As I have discussed earlier, the density, fluid velocity and the potential have got these perturbed terms. Now it is, I have written here n0 in order to give you a feel how it goes or changes over time. In many cases when you have a normalization with reference to the equilibrium value, then n0 by n0 it becomes 1 and all the terms are normalized. Here also, just in order to give you a feel, I have given it n0. Now what happens in a wave which undergoes nonlinear interaction and there is certain nonlinear interaction and the waveform changes, then we have to transform our coordinates x and t, the space and the time coordinates, with that of the wave. Suppose a wave is propagating with the velocity m. So the phase is kx minus mt. Now in such a case we stretch our coordinates or give it a transform. We often call it the stretching of variables. The stretching of variables, and you can see it is xi is equal to epsilon, where epsilon is a smallness parameter we discussed earlier, x minus mt, and tau is equal to epsilon to the power 3 by 2 t. Now these are the stretched coordinates, and therefore the derivative with respect to ddx or partial derivatives del x will be equal to epsilon to the power half del xi. Just check it yourself. Similarly, the second derivative will be like this, and the derivative with respect to time will come as epsilon to the power 3 by 2 del tau minus epsilon to the power half m del xi. Just check it by that chain rule method. Okay. Now in the continuity equation, just to give you a glimpse, here in the continuity equation, in the governing equation, we had n into u. So this both term had a perturbative expansions. N has its own perturbation expansion, u had its own. So while giving its a product, it will have some product kind of terms which we need to check. I need to show you. You see, n into u is the unperturbed terms, epsilon n0 u1 plus u0 n1 epsilon square. We haven't written the higher order terms, but remember here there will be three terms because the second order terms with the unperturbed terms will be here, and these were not the first order perturbations. Now substituting the transformed operators. What are the operators? The space and time derivative operators. And we have got into our new stretched coordinates, that is the del del xi, del del tau. And substituting the transform operators in the dynamic or governing equations, the continuity equation takes the form. You see, it was ddt initially, so it just got transformed into with this tau and xi variable, and this was ddx, which is only dependent on xi variable, now new variable. Now we have just written it in the expanded form. Why did we write it? Because we have to take out different sets of equations corresponding to different orders of epsilon. Now from observation of this thing, we can see that while we consider the derivative parts, the minimum power of or exponent of epsilon that will be valid to have different orders equation will be epsilon to the power 3 by 2. Why? Because when you take epsilon to the power half del del xi of n0, it gives you 0, it's a constant term. So the non-zero term for the first time it's come with that of n1, the first order perturbations. So epsilon to the power 3 by 2 m del del xi n1. Similarly, now let's take the different order equations of epsilon. Sorry. Okay. So the epsilon to the power 3 by 2 order of the equation is given by m del del xi n1 plus del del xi. You see, from here only the first order terms will come. These two terms will come. Okay. And for the next higher order, now you see we haven't taken that epsilon to the power 3 by 2 or 2 square because that won't come here. Had the perturbation expansion had a different series of epsilon to the power half epsilon to the power 3 by 2, because in such a case, let's go there. Let's come here. If the perturbation expansion had a different kind of expansion, suppose n0 plus epsilon to the power half n1, epsilon f to the power 3 by 2, or all the odd exponents of epsilon, then we would have got different orders there. Now here, since we have taken only the linear or the integral powers of epsilon, this will come in this form. Okay. So far we have checked epsilon to the power 3 by 2 and epsilon to the power 5 by 2. I think you people are referring to the handout with this handwritten note and just check it yourself. Okay. Now coming to the next page. Now the momentum equations, it will also get some this expansion on the left hand side. This, you see, the whole left hand side got is written in the extended form and is for the epsilon to the power 3. Now here we have just taken n, we have written it in because that would give you a bigger thing. Now here you see that n to the power gamma minus 2, where n to the power gamma minus 2, we have just simplified it. Some people might have used it n0 to the power gamma minus 2 and ignored all these things. Well, that's also possible. But you see, there are different ways to obtain the KdV equations. A lot of people make assumptions or approximations. Well, those are valid, but since we are just learning the technique, we are just showing you all the possible scopes of how to do the expansions and all these things. Now you see, we have just put it in this way, and there was one gamma minus 1. Now how did we do it? Let's come to the next. Suppose the whole quantity is written by the unperturbed term 1 plus the perturbed term. Now the perturbed term, as you see, it is written as epsilon, this whole series that we have perturbed part, the perturbations. Now n to the power gamma minus 1, you see this whole thing comes as gamma minus 2 and n star. Now we are just taking this part as the unperturbed quantity and we just expand this part. So this makes the work a bit simple. You can just apply binomial expansion and this will be more simple. So far the expanded momentum equations, as we have done for the continuity equation, the momentum equations, from the expanded momentum equation we get for different powers of epsilon to the power 3 by 2 and epsilon to the power 5 by 2. And you see here there was only first order terms, but for 5 by 2 we get u2 n2, similar to a continuity equations. Okay. Now for the Poisson's equation, you see we have written the perturbation expansion of the potential, and that del 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 2 del x2 was there, and we have just written in terms of xi, and we have just expanded it. Make sure that the ions here act as the background, neutralizing background. Why you call it neutralizing background? Because we are just, for this problem, for the sake of this problem, we are just considering them to be heavy enough to continue with any kind of oscillation. Okay, so at equilibrium condition, the quasi-neutrality condition, n0, which is the electron density, and the ion density, they will both cancel out. So we just cancel these two terms. Now note that the ion density, that's what I've said. Now from the Poisson's equation, taking different orders in epsilon, epsilon square del 2 del xi 2 of phi 1, it gives you n2, not n1. Note it. And similarly for the next higher order, it gives you the n3. Now taking the derivative, why I did it? Because in future we will need it, this kind of expression. Okay, this gives you the n2. Now from those equation 10 and not 13, just forget it, we just simplified u1 in terms of n1, because there was this derivative with respect to xi. Now you just, if you integrate with xi, in these terms cancel out. I am not talking about the constant term, because for the sake of these perturbations I am just taking into the integrand part. So you get a simplified version for u1 in terms of n1. Suppose call it rn1. Similarly from equation 11, that is for the higher order in the continuity equation, we get this expression. Now simplified, we just take the first order terms on the left hand side and the second order terms on the right hand side. This is done in order to eliminate. Okay, we are just going to eliminate the higher order terms. Now coming to the next equation, that is the first order term from the momentum equation. You see, this was the momentum equation with the first order term, and I have just written it simplified because I don't want to write all those things again and again. Now with this we get n1 in terms of phi 1. So you see, from the first order equation we don't get any n2 or phi 2 or u2 kind of terms, so it's a good thing. So we just get n1 in terms of phi 1. Let's call it p1 phi 1. Similarly from the previous page, as we have done here, u1 in terms of n1, we can also write the u1 in terms of phi 1, just we call it p2 phi 1. Yes, I have just kept it so simple, because all the time writing all these things is a really laborious work. It is just simplify it. Now coming to the next problem, C2, we have just made a mistake out here. I think so. Please excuse us. C2 would be the term. While copying, I think I made a mistake. C2 would be, yes, some term. But this would be your C2. Okay, don't mind. C2 and C1 are same. Okay, just so you get from the momentum equation all the first order terms on the left hand side, and on the right hand side you get the second order terms. Okay, now from these two equations you see from 17 and 20, that is the second order equations, or epsilon to the power 5 by 2 equations in the continuity and momentum, you write it like this. Okay, now you see on the left hand side you have got all first order, on the right hand side you have all got the second order terms. Now in order to eliminate these two, you have to multiply n0 with this one. It is minus and it is plus, so you multiply with n0 and multiply this one with m minus u0. So this term will be existing. First we have to just eliminate this u, because you have got that Poisson's equation in which you have got that density but not velocity. So just eliminate the velocity, that will be better. You just eliminate the second order term from the right hand side and get this elimination process. So rearranging and simplifying is the next step. So what we do it here, well, what we do it here is, in one we have just simplified it in terms of phi 1, because you have got your three equations and you have three variables. What are the three variables? N, u and phi. So you have to just bring down in terms of phi. Now while you write it, I have just made some simplifications. Del phi del tau, del phi 1 del tau with this quantity. Del phi, there was two terms, you see. Here there was n1 u1 and u1 square. We have just made it. So divided by 2, because there was this term. Let me check here. Yes. Here it was n1 u1 and it is u1 u1. So when you multiply with that phi 1 term or substitute with this phi 1, so it becomes phi del xi, and this becomes some constant times del xi of phi 1 square. So when you differentiate phi 1 square, it gives you by 2 phi del xi. So that's the thing. Okay. Now writing this simplified in this form, we get this all the first order terms on the left hand side, and the n2 the second order term, and the phi 2 in the second order term. Now this n2, as I have told you, from the second order uh, power of, or second higher power of epsilon, that is epsilon to the power 5 by 2, from Poisson's equation, we substituted this n2. How? We got this expression. We differentiate it with respect to xi once again. So del n2 del xi, we get del q, del 3 phi 1 del phi del xi cube. So you just put it here. Okay, and the only term that remains here is this one. Now from 15a, there's the epsilon to the power 5 by 2, or no, epsilon cube, I think, or the second higher order in Poisson's equation. We find that we integrate this term. This was del 2 phi 2 del xi 2 was n3. Now del phi 2 del xi is the quantity that we require here. Now we just integrate it with respect to xi. Now xi is the extended stretching coordinates. Now when xi tends to infinity, this term can be neglected, because those are the higher order corrections and the minimalistic changes will be there compared to all these terms. Okay, all these terms. So we just ignore that term. This term is ignored. So finally, with those equations and using the condition from the Poisson's equation, and we get this kind of expression for the this is the expression for the KdV equation. It's written in the extended form. You see, this is a constant, this is a constant, this is a constant, depending upon your initial values and the wavefront velocities. Now you divide it with this thing and you write it like this. You simplify and write that phi 1, you call it psi, just for your ease of mathematics. We write it psi del tau plus n psi del xi plus d del 3 psi del xi 3 is equal to 0. Now why did I write n and d? I don't have any liking for n and d, because n is the non-linear term and d is the dispersive term. You see why it is non-linear? Because a power of psi is here not 1, so it is non-linear term, psi del xi, and this is the dispersive effect or the dispersive factor that you can refer to your literature that will supply. Okay, so where n is the nonlinear coefficient, we have just, now you see this expression or this equation is derived in a number of ways. We are just taking one of the simple cases, and with those assignments that you will be supplying you with those assignments. You practice and you will get your KdV equations. Equation 25, this one is the KdV equation. Okay, so thank you. I hope you have just understood in a short way, and just let me recapitulate from this. These are the general governing equations. Let me put it in one place. We have got the governing equations, we have the equation of state, we have the perturbation expansion, we have the stretching of variables, we have the transformed differential operators. We put the transformed differential operators right in the extended form, arrange for different orders. We have just taken epsilon to the power 3 by 2 and epsilon to the power 5 by 2 because we are not going to the higher order terms. Because if you take higher order terms, those will give you higher order KdV like equations. Equations which are like KdV but modified. So we call it modified KdV equations. And different mm, forms are available in the literature, and you can just check it if it's possible for you. Now you have from the momentum equation, from the continuity equation, you get this expression, and for the different orders of epsilon. For the momentum equation also you get these two. We have just told you how to simplify that nonlinear terms or the perturbed terms in case of density. And from the Poisson's equation you get for first order. Here you don't get epsilon to the power 3 by 2 because it's already second derivative. So it becomes epsilon. So the first quantity of epsilon with which is differentiable is del q phi 1 del psi q, and it is the second order, so it's given to q and not to the power 5 by 2, mind it. And we have just considered that at equilibrium this electron density and ion density, they are same, so cancel out. So just substitute and eliminate from those first order epsilon to the power 3 by 2 equations from continuity and momentum equation. We solve and get this expression. Similarly for the first order elimination, and it's the second order elimination from the continuity. Also from the momentum equation we can write it like this as we have just discussed. And for this excuse me, for this quantity I just missed it, and you just substitute, eliminate, and finally you get this kind of thing. Multiply this, and I told you to eliminate this velocity component because velocity is not in our equation, that is the third equation. It's only with the density, so just eliminate this velocity and finally use your boundary conditions or the long wavelength approximation, where you find this as a form of KdV, and finally you simplify it in this form. So this is your KdV equation. Thank you. Good night. So in the next lecture we will be dealing with how to find the solution of the KdV.